Imagine that the material beneath our feet, supporting our cities, bridges, and buildings, is the second most utilized material after water. Concrete. The world consumes more than 30 billion tons of concrete annually, an extraordinary figure that illustrates how dependent our daily lives are on this fundamental material. From the ancient pyramids in Egypt to Roman amphitheaters to modern skyscraper in Dubai and in New York, every civilization, ancient or modern, has built its legacy upon a foundation of concrete. However, behind this remarkable achievement lies a concerning reality that often goes unnoticed. The concrete production process is responsible for approximately 8% of global carbon dioxide emissions. We are civil students of Helwan University, and in this presentation we will discuss methodology for improving concrete properties while making it environmentally sustainable.
CMS definition. Supplementary cementation material are specialized additives that can be added into concrete mixture to reduce depend on usual cement and enhance concrete properties, including reduce emission and extend the surface life. CMS include fly ash, a product of coal composition process utilized to enhance concrete resistance and reduce permeability. Iron slag, generated during iron smelting operation. This material significantly improves structural strength and resistant properties. Silica foam, a product of silica manufacturing, contributing substantially to improve tensile and decompressive strength. Comparative analysis of supplementary cementation material. Fly ash, known by its economic viability and widespread availability. However, it may exert limited influence in initial strength development. Iron slag, added good strength properties and enhanced temperature regulation capability, particularly suitable for high-performance concrete application. Silica foam delivers significant improvement to mechanical properties at higher cost and require precise mixture management.
Here are the steps we will use to reach the optimal ratio. First, research, data collection and understanding material properties, then the experimentation and trial phase, and finally reaching the optimal point. We use two types of mixtures, BCS, which is the base case scenario, without using supplementary cementitious materials, and the second mixture, ACS, alternative case scenario, where we will replace a portion of cement with a proportion of supplementary cementitious materials. Here, the proportions used in both mixtures are as shown in the table. The ACS mixture has variable proportions of supplementary cementitious materials, while the BCS doesn't contain any proportions of supplementary cementitious materials. Regarding materials locations, the distances between the university and material sources are relatively close, because Egypt is characterized by the abundance of raw materials, such as sand and gravel, components of cement, due to the desert nature of Egypt. Experimental methodology and results. Our research team conducted multiple experimental trials to determine optimal SCM proportions, utilizing life cycle assessment methodology and Life 365 software. The results demonstrate that fly ash incorporation yields minimal environmental impact, while modestly extending concrete service life. Conversely, silica exhibits higher environmental emissions compared to fly ash, but substantially increases concrete longevity. Regarding the limited utilization of slag in our research, our findings indicate that slag demonstrates moderate effects on both environmental emissions and concrete service life extension.
The ideal ratio. After experiments and the results obtained, we concluded that the ideal ratio is 30% fly ash and 9% silica. However, this gives an life cycle assessment value lower than the permissible value. Therefore, we concluded that a ratio of 38.178% fly ash and 1.822% silica gives an ideal result. At the environmental level, an average ratio of 15% gives the following indicators. At the concrete lifespan level, the concrete lifespan will double to 2.3 times the original concrete lifespan. Results of environmental impact using life cycle assessment tool. The figure shows environmental indicators and reducing environmental impact by an average rate of 15%.
As we mentioned before, Egypt has plenty of raw material for concrete because of these are natural. This makes the distance between sources and construction site relatively short. For cement, nearest cement factory is Tora Cement. It is about 0.8 kilometers away from the university by road. For aggregate, sand and gravel, the nearest quarry is on Bilbis Road. It is about 30.8 kilometers away from the university by road. Quarry is on Bilbis Road. It is about 30.8 kilometers away from the university by road. CO2 emissions from Egypt's cement industry, 54 million tons of cement as a secondary product. In 2022, Egypt's estimated carbon dioxide emissions are around 254 million tons of cement as a secondary product. Carbon dioxide emissions from cement are about 30 million tons.
How to increase use of coal fly ash? First, Egypt annually produces approximately 2 million tons of fly ash byproducts, but only 500,000 tons are used. Only 25% contains higher than 70% of silicon oxide and aluminum oxide. And the sources of fly ash in Egypt. Most famous is the Hamrawiyah power plant located south of Safaja, among the largest coal-fired plant in world, and the Cairo power plant, one of the largest coal power plants in Egypt. So how to increase use of coal fly ash again? First step, collaboration with major cement plant and reduce costs. Second step, government regulation and incentives to encourage substitution. And mandating 20 to 30 fly ash using in cement plant. Positive impact on Egypt. So, positive impact on Egypt. Using fly ash helps reduce the carbon emissions in Egypt by 3% to 5%. It also helps lower cement production costs. Finally, we have finished our presentation. Thank you for your time.